as you call it now. Okay, let me try to explain more clear. I recall exponential function. Exponential function is y equal ax. Remember the variable, the independent variable is exponent. This is the exponential that we studied last class. However, if you want to find the inverse, the only thing you should do is interchange x and y in any function. So now it's x equal a to the y. Boom. This is the inverse. The only problem of the inverse is that this inverse is implicit. Remember, implicit form is when the y is not already isolated. And this is not good. So in order to express it in explicit, is clear, so explicit is inverse again, and explicit. Well, we apply that notation. Look, you say y is equal log, is the name of the function of the base a of parenthesis x. This is similar to the function notation, but this is a special function and have a special name, is log. Look, it's the first three letters of the logarithmic function. Okay? This is a definition, but professor, I don't understand anything. What is the interpretation of this? Okay. This is the idea. Look, interpretation. And today we are doing a lot of example of the logarithmic function. Interpretation. Suppose that we have two different, let me split the board in two parts. In that part, I want to write exponential statement. And the other hand, in the right hand side, logarithmic statement. And you can see how we transform or change from 1 to 1. So the exponential to logarithmic or the logarithmic to exponential, because it's reciprocal, no, in both directions. Suppose a straightforward example, elementary, kindergarten example. Suppose we have 2 to the 5th power is equal to 32. This is clear because the base is 2, the exponent is 5, the result is 32, because 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is 32. Oh, easy, I understand. However, when you change this to the logarithmic statement, you put the magic word log, you specification using a small number, the base case 2, you put something inside the parenthesis, and the result, the answer is exponent, get 5, and 32 here. Okay, so what is the interpretation of the logarithm? Well, logarithm always give me what exponent is necessary to raise the base in order to get the number inside the parenthesis, get 32. Okay, repetition. The logarithm, the answer of the logarithm function is always the exponent that is necessary to raise the base in order to get the result. Okay. You understand a little bit, not too much. Suppose another example. Suppose 3 to the 4th power is equal to 81. This is again exponential statement. Because 3 times 3 is 9. 9 times 3 is 27, and 27 times 3 is 81. Perfect, no problem. I put double arrow because we can do in different direction. No? And you put the magic word log, The base is obvious que 3. Look at that. Inside the parentheses, you have 81. Que 81 represent the result of the exponential. Now it's no result, it's the argument. And the answer is 4, get the exponent. So what exponent is necessary to raise the base 3 in order to get 81. This is the idea. Okay? I bring more examples. Look at that. Suppose in the test, I give you different, a little bit. Suppose I give you in that way. Logarithm base 4 of 64 is equal, well, I have no idea. Because I have no calculator. To say, I don't know working exactly with the calculator. And we are learning new logarithms. I don't understand very well. Okay, so now, to find the exponent, well, you are doing the transformation in that direction. So I ask by myself, what is the base in this statement? Oh, it's 4. I put the big 4. What is the exponent? I have no idea. X is equal, the answer is 64. Because basically the answer of the logarithm is the exponent. Who the exponent, you need to raise the base in order to get 64. Okay, so in that moment, you have in front of the one exponential equation, exactly we studied last class, and you've tried to find the common base. One of the common base is 4. 4 to the x, and this is 4 to the third power. Because 4 times 4 is 16, and 16 times 4 is 64. Therefore, the solution is x equal 3. And this is a fantastic way, okay, I want to explain now, to solve this equation using the transformation, but not in this direction, in this direction, convert to logarithm. But okay, the most important objective now is that you understand the interpretation for the logarithmic. Okay, I repeat one more time. Logarithmic give me the exponent in which you need to raise the base in order to get the value is the result of the exponential. Suppose, let's practice with the base 10 is easy. Suppose logarithm base 10 of 1000. Have no idea. Logarithm base 10 of 1000. Well, okay. Sometimes happen, this is frequently happen. Okay, you don't know very well the logarithm statement. However, to see much better, you convert to exponential statement. What is the base? Oh, the base is 10. What is the exponent? It's exactly I am looking for. I have no idea. And the answer is 1000. I know very well that 1000 is 10 to the third power. Therefore, if we have two exponential and the base is the same, it's because x is 3. So by coincidence, this is the same result. It's a coincidence. I don't know. For example, logarithm base 10 of 100. What do you suppose is that? Okay, this is easy by hand. No necessary calculator. Using the same idea. Opinion. Come on. I asked you. Any answer? Logarithm base 10 of 100 is? No idea? Hey.
2.
Are you there?
2.
2. It's over to 2. It's over to 2. You're right. It's over to 2. Okay, suppose I have no idea. Okay. I convert to exponential. The base is 10. The exponent, no, I don't know. And this is 100. Yeah, I know the 100 is 10 to the second power. Therefore, same base, x equal to. What about logarithm of base 10 is easy to 1 million? Using the same common sense. Remember, this was 3. This was 2. And this was
6.
This is easy because you see how many zeros we have in 1000. 1, 2, 3. How many zero we have in 10? 1, 2. Well, how many zero we have in 1 million? 1, 2, 3, 4, 5, 6. That's 6. But no, it's too easy. No, it's too easy. For example, what do you think about logarithm base 10 and continuous base 10 is easy by hand of 10? What do you think? Logarithm base 10 of 10. What do you think? Using the same idea, the same logic. No idea? Nobody? Come on, guys, try to. One, it's obvious. How do you know que one?
Because 10 to the first power is 1.
Exactly. Okay, exactly. Because 10 to the 1 power is equal to 10. This is exponent I am looking for. And this situation happens always. Suppose you have logarithm base 2 of 2. 1. Logarithm base 3 of 3 and 1. So when the number in the base is a coincidence with the number inside the argument, the answer is 1. It's obvious. But what? I have more. Suppose that we have logarithm now, base 10 again, que is easy by hand, of 0.1. So decimal. Less than 1. What do you think? No idea? Nobody? I know it's a little bit tricky, huh? Nobody have idea what's the value for this? Logarithm base 10 of 0.1. Okay. Me too. I try to do. How I can always change to exponential. What is my base? My base is 10. What is the exponent? I don't know. It's exactly. What do you say, mister? I don't see the chat now. Entonces 0.1. 0.1 here, right? This is my equation. But 0.1 is 1 over 10. Reciprocal, no? The 10 is. But reciprocal 10 is 10 to the minus 1. Wow, same base as 10. Therefore, the answer is x equals -1. Do you see that or no? Do you follow me? Do you follow me the idea for the behind the logarithm? Today is without calculator because it's a straightforward example. Now, no. Now, after that is more complicated. It's impossible by hand, and we need calculator. Okay, what do you think about logarithm of 0.01? So this is 0.01. So 1 decimal more after the decimal point. What do you see using the same idea? This is -1. And this is using the same common sense.
-2.
Exactly. Very well, mister. And logarithm base 10 of 0.001. And instead of 2 decimal place, 3 decimal place after the point. Come on, it's the same, no? How many decimal points we have? 3, no? Then it's negative. Do you follow me, guy? Or confusing? Come on, opinion. Today is the day to study the conceptual idea behind logarithm. You need to understand what the hell is that. Okay? What is the meaning behind this concept? Logarithmic. Logarithmic give me always the exponent. You define the base, you define result. So in general. Look. What is the formula? What is the formula? Okay, I can explain. I can explain like that. Look, we have the classical exponential que have a base raised to the exponent equal, let me call result. When you transform it, this statement to the logarithm statement, okay, I put the LOG. is the name of the function. You put the small number here, get the base, same copy paste. You put it inside the parentheses of the function notation result of what? Of the hypothetical exponential statement, equal exponent. It's a rule. Okay? Okay. Entonces, you need to be aware to transformation any statement from exponential to logarithm or logarithm to exponential in both directions. This is part of the game in this test. Let's do another example. This is important. Look. Suppose I want to compute logarithm base 10 of 1. Logarithm base 10 of 1. I have no idea. Es equal X. Well. See, somebody have idea? Where's the answer? No? No problem, I understand. Okay, so I propose you change logarithm statement to exponential. Where's the base? Where's the answer? No, I don't see the chat. And I have opened the whiteboard. The whiteboard cover up the chat. So, activate the microphone and you say the answer is professor something. Okay, let's do it. Remember the key idea. What is the base? The base is 10. What is the exponent? I don't know. Equal 1. So what is the exponent I need to use on the same base? It's 0. Because I know very well any number raised to the 0 power is 1. Therefore, X is 0. Wow, fantastic. So I can see one important property. In this example, look, this and this and this gets a number greater than 1. And even this, the answer for the logarithm is positive number. In this example, let me using another color. This example, and this example, que the number inside the logarithm is less than 1, the answer for the logarithm is negative number. The logarithm cover positive number and negative number in your range, but not in the domain. And one particular important, super important property you need to know from now is the logarithm of 1 is 0 regardless the base. Suppose logarithm base 2 of 1 is 0. Logarithm base 3 of 1 is 0 because it's 1. And this makes sense because you remember the universal point in the exponential, que is the point 0,1. This X is a Y, but the universal point in the logarithm is exponential. But the logarithm is log function is 1,0. Okay, remember that the only thing you are doing is interchange X and Y. X is 0, Y is 0. Y is 1, X is 1. Okay? One more example before the study in detail the logarithmic function. This is just introduction, interpretation, what means logarithm. Okay. But I want to explain in detail the idea, the property, no, for the logarithmic function. Okay, one more example. Suppose it's a little bit complicated using your imagination. Suppose logarithm base 5 of the 1 over 125. I have no idea. Without calculator, and the calculator is easy, but without calculator. And logarithm base 1/2, wow, of 4. I have no idea. And the base, remember, the only restriction with the base is no 1, no 0, or no negative. So it's impossible to have negative base. This is totally illegal. out the domain. Okay, entonces I have no idea. It's hard for me without calculator, professor. But okay, I can change to exponential. Maybe when I change to exponential, I see much better. No? The base is 5. The exponent, I have no idea, is equal to 125. This is the exponential statement associated with this logarithm statement. And maybe using a little bit algebra, a little bit arithmetic, we can discover what the value for the x. I know. Okay, 125 5 cubic, no, is 5 times 5, 25, 25 times 5, 125. Go ahead, perfect. And this reciprocal. See, reciprocal is negative. You can write 5 minus 3. Wow. If the base is the same, it's because the exponent is the same. The answer is negative 3 in this example. And make sense, everything matching perfectly with the idea that when the number inside the argument is less than 1, the answer of the logarithm is negative. Okay? But this is under the condition that the base is greater than 1. Base greater than 1, argument less than 1, answer of the exponent, the logarithm, is negative number. However, in this example, occur completely different idea. In this idea, the base is less than 1, and the number in the argument is greater than 1 before, no? Okay, so something weird happened, I know. Si imagine greater than 1 both or less than 1 both, it's okay. But si it's different, no. Okay, so let's do it. Let's transformation this statement to logarithmic, to exponential, sorry. The base is 1/2. Look, I copy that number here. The exponent is x, and the answer is 4. How you solve this exponential equation? Well, you find the common base, and the common base in that case, I suppose is 2. Because 1/2 is 2 to the negative 1, x, and 4 is 2 to the second power. Now, multiplication of the exponent, this is like a 2, no necessary parentheses. No necessary parentheses. 2 negative x, negative 1 times x is negative equal to the second power. So we have 2 exponential, the base is the same, so the negative x is equal to, conclusion, x is negative 2. And this happens again because we have a contradiction. Base less than 1 and argument of the logarithm greater than 1. Here occur exactly the opposite idea. The base is greater than 1, 5, and the argument is less than 1. So the logarithm is negative. Okay, so this was the quick tour for the interpretation for the logarithm. I suppose que no is not enough. Okay, we complete the idea now. We just study in detail the logarithm function in detail. And also, we continue in the review. So from today, we're using the calculator after, not today, but next week. Okay. What's going on? Okay, again. This is a new whiteboard. It's a little bit complicated for me. Okay. Come on. Delete. Wow. No delete? Yes, delete. This is have some time delayed. Okay, let me make a zoom to see more clear. Okay, guys. Now we study in detail the property of the logarithm function. Property of logarithmic functions. Put in plural because it's a family of the function. It's not only one, but it's a family because depends on the base que you assume. So now to do that, I propose you do the graph of the logarithm function. Oh, but this is easy because I know very well the graph of the exponential function that we studied last class. And remember, graphically, it's good idea to visualize the main range, etc. Okay, suppose. I remember, for example, I want to study one particular, easy, not complicated. F of x equal, go ahead, logarithm base 2 of x. So the base assume que es 2. Si es 3, si es 4, si es 5, let's see after. But this is my first example. I try easy example. Then I recall very well the exponential associated with this. It's a function, let me call it different name, no? G is 2 to the x. And the function 2 to the x have different points. The universal point is this point, 0, 1. Because when the x is 0, any number raised to the 0 power is equal 1. Another important point is x equal 1. So the fundamental point is x equals 0, y is 1, x equal 1, y is 2, because it's 2 to the first power, so 1, here another point. Suppose another point, suppose y not 2, x equal 2, y equal 4, because it's 2 to the second power, it's 2 to the 4. And this look like my exponential function. And the positive part. And the negative part, it's different. Negative 1, y is equal 1/2, because 2 to the negative 1 is reciprocal. So here, over there. Or x equal -2, is 1 over 4, and so on. 1 negative 3 and 1 over 8. And this approaches this. I remember also that with our exponential function contain one horizontal asymptote at y equals 0 without transformation. Okay, I did that. Okay, understand. Now let's do the same idea in logarithmic, because our goal. Our goal is this. Now, okay, super easy, because the idea behind is that you is the inverse function of this. Therefore, you interchange one more time x and y, point by point. At this point, guess the point, 0,1 would be here, 1,0. This point, sorry, case 1,2, and the logarithm associated with this would be 2,1. Interchange x and y. One more. This point, the original was 2,4, and the logarithm function will be 4,2. 4,2 here, 4,2. And at least in the positive part, the logarithmic function look like that. I promise that I want to put in decimal now to see super elegant graphic. Okay, this is the function log base 2 of x, and this is the function 2 to the x. Okay. And what about the negative part? And what about the part less than 1? Wait. Remember that point. That point is the point -1,2. This is in the exponential, and the logarithm is 1/2, -1. Boom, here. 1/2, -1. And likewise, -2 is 1 over 4. And you see how our function approaches, but never touch the y-axis. And the reason can never touch is because the logarithm function have vertical asymptote at x equals 0. This is no surprise, because when you study the inverse function, you can see in the last example that the horizontal asymptote in the function, when you find the inverse, become like a vertical. And likewise, happen. Si es vertical, horizontal. So switching, swap the accent. And you can see one more time que that function que es inversa is symmetric with respect the identity function, que es the line y equal x. No secret. It's the same theoretical thing that we studied in the first topic of this chapter. But I see more detail. Wow, 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 wow. See, I asked you, for example, what is the domain? What is the domain? What is the domain of logarithmic function? Look at the graph. Of course, the blue, que es el logaritmo. You see when you any point on the graph is projecting onto the x-axis, you see que es from 0 to infinity. We have no negative projection. Therefore, the domain is 0, infinity. And 0 no included because it's vertical asymptote. And this approach pero never touch. Okay? It's a no surprise. It's a no surprise. Why not? Because si I recall quickly, domain and range of the exponential. Look here, I copy here, exponential. Domain of exponential or real number. Nice function. No problem, no restriction, never. And range of the exponential is 0, infinity. This is for exponential function. And for the logarithm function, you know, the action is interchange x and y, like that. Look. Therefore, the domain of the hypothetical, the range of the hypothetical exponential passing through the logarithm, the domain of the logarithm, and the range of the logarithm is now the domain of the exponential. Is from negative infinity to positive infinity. Wow, it's logical because when you're projecting the blue curve onto the y-axis, we cover positive, negative, and 0. Look, logarithm 1, let me make it zoom. Logarithm 1 is 0. Look at that. Here, 1,0. Logarithm of the number greater than 1 is positive. Logarithm of the number less than 1 is negative. And never we have nothing here in that quadrant. Therefore, you need to be aware. This is a moment to say that the logarithm of 0 and logarithm of any negative number is completely undefined. It's completely out the domain. Because domain includes from 0, no 0, so no 0 to infinity, so only positive. So the logarithm only accept inside, I need the specification, the base, 3, 4, 5. Accept only positive 50, for example. And this by hand is hard, but we use calculator. Okay, this is the two important property, domain and range. Anytime we study a new function, you need to define domain and range, right? And what about x in a set of the function? Well, it's this. It's the point 1, 0, always. Regardless the base. Doesn't matter if the base is 2, or 4, or 5, 10, whatever. So you say what is the y in a set? No, we have no. Because the curve, the blue curve, of course, never touch the y-axis. It's asymptotic. Okay. Another property is if the base is greater than 1, the function is increasing. The function is increasing. It's exactly the example we are doing. Because I suppose in this example we are doing now, no after I did another. Okay, the base is 2, so 2 is greater than 1. And the function is increasing. Remember the way, fantastic way to interpretation that the function is increasing. You travel on the curve with the roller coaster car As the roller coaster car goes up, it's obviously increasing, no? Never goes down, it's increasing. However, I want to prove in a few minutes that if the base is less than 1 and 0, remember the base never is negative, it's in between 0 and 1, the function is decreasing. And you see now this more clear. Okay, so now important, super important point. Super important. I know. Well, number 6 is clear. Is the logarithmic graph it has one vertical asymptote at x equals 0, always, anytime. And finally, number 7, the typical point. Okay, we're using to do the graph. Typical points. Typical point are, for example, the universal point. Universal point. They always in the logarithm is 1, 0. And you're using another point is the base a, 1. You know, logarithm of 1 is 0. Logarithm base a, I suppose. Logarithm base a of a is 1. You see that, right? And the reciprocal of the base, -1 is because logarithm base a of 1 over a is -1 because it's reciprocal. Okay, keep in mind this idea. Keep in mind this idea. Entonces now in the test online, on paper also, typical question is do the graph of the any logarithmic function. Suppose in the test I put here for you. Plot the graph of the function y equal logarithm base 5 of x. Or maybe 4, or maybe 5, or maybe 1/2. Okay, professor. I know that our graph contains one vertical asymptote here. It's 0 on the y-axis. This is x equals 0, it's a vertical asymptote. And the 3 typical point is the point 1, 0. Universal, I plot that. Another typical point is the base. The base is 5, 1. Or this is 2, 3, 4, 5, 1. That point is the point 5, 1. That point was the point 1, 0. And another typical point is the reciprocal of the base gets 1/5, -1. So 1/5, I don't know, approximately using my imagination, you divide this segment in 5 portions. I suppose get here, -1 here, approximate that point here. This point is the point, 1/5, -1. And our graph look like that. Okay, increasing, but increasing too slow, not fast. Logarithm increasing too slow. It's a function increasing too slow. Okay, don't worry, be happy, because we continue doing that. In the review package, I reinforce again this idea, right? Okay, so I propose you now go to Desmos to see more clear this idea. Okay, look, Desmos. Let me share the screen to see Desmos. Boom, boom. Okay, do you see Desmos? Look. Well, let me start at the beginning. Boom, boom, nothing. The first x exponential. This exponential is 2 to the x. Okay, we see before in the last class. In this example, this is the logarithmic function. Boom, and include the identity y equal x function. Because I know that this is behave like a mirror, and this point green is symmetric with this point blue. And the curve is, let me change the color. The curve of the exponential is blue. I want to change to green. Green is exponential, and blue is logarithmic. Do you see that? And you very well understand the correspondence. For example, this point is 2,4, and the logarithm is 4,2. This point is 1,2, and the logarithm is 2,1. This point is a famous universal, 0,1, and this is 1,0. And this point is negative 1,1 half, 0.5, look at that. And the image of this guy is 0.5, and so. Okay? That's it, no? No, because we analyze in this graph only when the base is greater than 1. So what's going on if the base is less than 1? Let's see. Everyone follow me, guys? Sure or no? Totally lost? Huh? Everything okay? Are you sleeping? All right, you're aware? Okay. What do you say, Dylan? Follow me. He said, okay. He said, follow me. Okay. Opinion, guy. Clear. Okay, let's come back again to the decimal. Do you see decimal, right? Mm-hmm. I want to do the graph of the exponential, but the exponential when the base is 1/2. Let me show you. Yes, there you go. Boom. This is decreasing. This is decreasing. This is decreasing. Okay, for example, it's like an image. The exponential when the base is 2 is look like that. Let me show you. Boom. But I don't care this now. I care when the base is less than 1/2, for example. Okay, good. And what about the logarithm associated with this? Well, the logarithm associated with this is this. Boom. Look at that. It's symmetric point by point with respect to another. Let me change the color. Let me put, wait a second. Here over there. Let me change to black color. Black color. Black color is logarithmic. And brown color is the exponential. Suppose this point 0,1 is 1,0. Suppose this point, que es negative 1,2, here would be 2,-1. 2,-1 is that point. Look, it's the image of this. Symmetric with respect to that. Okay. Entonces es similar, except that the function is decreasing. And when the base is less than 1. One more important, something. You can see again que logarithm 1 is 0. Logarithm of the number, in this case, greater than 1 is negative. Look, negative 1, negative 2. And logarithm in between 0 and 1 is positive. 1, 2, 3. Okay, it's completely opposite idea. When the base is less than 1. Good or not good? Okay, let's come back to the whiteboard. Okay, let me share the screen. Whiteboard now, because I want to discuss another important thing now. Whiteboard. Okay, super. Let me erase totally the board. Okay, let me try. No erase. Wow. Like that is not good. Let me try another way. No, all of them. It's partial eraser. Good. Okay, good. Okay, so in our calculator, next week, of course, we are working with standard logarithm. You see one professor, what base I select 2, 3, 4, 5, 6, 1/2. No. We have a standard. So in our calculator, when you buy what you have right now in your hand, logarithmic functions, we have two standards. The first standard is called common logarithmic. In this case, the base is 10, exactly the same of the example that we were doing before. Entonces the representation is log 10 of x, right? This is special using in science, chemistry, physics, and so on. Science. By the way, it's important to say in the calculator you see only log, because when you are working with the common logarithmic, you suppose default get the base is 10. And you don't need to specification that thing here. No. When you see logarithm without specification of the base, it's because of that. End the story. Okay? Now we have another very useful, is natural. Natural logarithmic. A natural logarithmic, the base is E. What is E? E is a famous irrational number. E is a famous irrational number. And the definition of this E is equal this expression, 1 plus 1 over x raised to the x, and x approaches to infinity. And this give me E. And E is irrational, and any irrational number contain infinity decimal number non-repeated. So it's approximately 2.7182818, and this continue for. But this is using in calculus. So the logarithm that we use in calculus, the student can need to take calculus. And any logarithm that frequently we are using in calculus because have a huge advantage using natural. And the representation is log of E x because the base is C. But the default, everyone in the world, no like that. No, it's not like that. LM, 2 letters of x. So LM is natural. So, and that's it. Natural logarithm, LM. LOG, common logarithm, base 10. Default, everyone in the world knows that. And in our calculator, suppose that this is my calculator. You promise that you bring the calculator next week, right? So Tuesday, next week, we are working with the calculator. We have one key here and one key here. This key, the name is log, is this guy. And another key is called LM, is this guy. And here in the same key, we have 10 to the x and e to the x, is the exponential associated with the same. And you select the function for this key using shift. Here, shift, you press shift and you press the key and select the exponential. See, shift first. Si no shift, directly logarithm. Okay? Entonces, es important because we are doing example. Entonces, I put in the board and you compute and you give me the answer. And we practice it step by step. Okay? Do you understand? Okay. Entonces, normally, in science calculus, we study using standard. We are working using standard. Logarithm, no base 2, no base 3, no base 4, no base 5, no, it's base 10 and base E. And the notation is log and LM. LM. Okay, super. Okay, now super important moment. And this important moment we studied in detail some fantastic property of logarithmic. Okay, this property help me to manipulate the equation. Remember, we manipulate the equation and after we solving word problem. This is important. So the application of this, the application in physics and chemistry and biology and finance, money. Okay, there are several applications. But okay, first of all, to manipulate this equation, we need to know that property. To set that property, number one property. Everyone know. Logarithm of the any base of 1 is equal to 0. Wow, I know that. Okay, when inside the argument you plug in 1, the answer is 0, regardless of the base. Example, logarithm of base 2 of 1 is 0. Logarithm of base 3 of 1 is 0. log of 1 is 0. ln of 1 is 0. Okay, when the argument is 1, yeah, directly, the answer is 0. Number 2, see the base is the same value of the argument, the answer is 1. Example, logarithm of base 2 of 2 is 1. Logarithm of base 3 of 3 is 1. Logarithm of 10 is 1. And ln of e is 1. Because they are perfect coincidence in the number inside the argument on the base. Property number 2, don't forget. And property 3 and 4. And property 3 and 4 is similar because it's the composition of the exponential and logarithmic function together. And I remember that both functions are inverse each other. Therefore, I know that the idea. When you form a decomposition and between inverse and the original function, the answer is identity function. The idea behind this is clear. It's because one function undoes the another function and doesn't cancel out. And the answer is identity, get nothing, right? We come back to the same number. Similar situation happen specifically in this function. Suppose we have the base exponential, and you put in the here in the exponent logarithm of the a. Wow, the answer is x, because mentally you cancel out this and this function. I don't like to do it this way, but this is the idea. Likewise, so you have, for example, logarithm of first. They say an exponential inside. Same situation. This is exponential and this logarithm cancels out. And the answer is x can represent the identity function. Okay, this is property 3 and number 4. We're using, no too much, but we're using that property. The most important property is number 5, number 6, and number 7. We use it every day. Every day we use that property. Look, property number 5, property number 6, and property number 7. We study 3 simultaneously because we are using every day. Okay, what's the idea? The idea is logarithmic of the any base of the multiplication to expression. Suppose that m and n is 2 expression. We can expand into logarithm addition. Wow. Multiplication is addition and the word of the logarithm. Division is subtraction. Of course, m is in the top is positive and m is in the bottom and negative. And when you have logarithm of the any base of the one expression, I call M again, but we have exponent. That exponent go to the front as a factor like that. R log A M. And this is magic. Why? Because convert exponential equation to linear equation when you move this guy in the front. Easy in the tail and your moment. No, now. Okay, those are 5, 6, and 7 we're using every day. Every day. Okay. One more property to finish the properties. Is a total is 8 property. 1, 2, 3, 4, 5, 6, 7, and 8. And 8 is also beautiful. And it's beautiful and it's received a special name. Property 8 is the change of base formula. Entonces now this formula magic because allow us to compute any logarithm we using calculator. So the logarithm I ask you using intuition, no, you put in a calculator, that's it. But I know with the calculator we have only the standard base. But our calculator contains only standard log and lm. I suppose I want to compute, for example, logarithm of base 3 of 81 using the calculator. In our calculator, we have no, in the most of calculator, we have no non-standard base. We have 2 standard base only. There are some calculators, yes, we have. But okay, no es the majority of this. Okay, so we're using the formula, the chain of base formula. Let me copy the formula after we apply in the example. The formula say logarithm of the base is given of the one number I call x is equal logarithm of the another base. Okay, for example, we have in the calculator to the same number divided by logarithm of the same base of the number n a, get the base. So you transform this using the formula like log assume this the base is 10, and the base is 10, not necessary to put 10 here, you know. So logarithm base, common logarithm, of course, of 81, 1 divided by logarithm of base 3. And you put in typing in the calculator. I promise next class we start doing this example, another example also. You put in the calculator, you press the key, log, parentheses. When you press this key, is log automatically. In the display, you see log and open the parentheses. You put 81, you put division divided by, you press the key again, log, you put 3, you press enter, and you get the answer. Okay, by the way, the answer is 4. In the display, you see 4. Okay? Well, the only possibility we have is using the log. No, we're using both. The logarithm you prefer. See, we using ln, the idea is the same. It's ln of 81 divided by ln of 3. And we get exactly the same answer, guys. This is fantastic. This is fantastic. So the time we have now, we practice a little bit. We practice a little bit easy example in which you apply the property 5, 6, and 7. Miscellaneous example in which you practice the property 5, 6, and 7, case conversion, multiplication to addition, conversion, and this property we can use it in both directions. We can use it in this direction. Look, when you want to expand, but we can use it in this direction when you want to condense the logarithm in only one. Suppose we have several logarithms, 8 logarithms, addition, subtraction, and you condense it in only one logarithm. Okay, and this is super useful to solving complicated equations. Okay, let's practice that. Suppose, let me try to find one interesting. Okay, this is interesting. For example, suppose we have, this is easy. Let me start for this. Suppose logarithm of base 5 of x to the 5th power divided by y to the 6th power. And what they want? Well, they want you write as a sum of differences of logarithm and also express the power as a factor. So basically you apply the property 6, and the property 6 says log of the any base, k1 kf5 of the m divided by m is equal log of a m minus log a of m. And also you apply the property 7, the property 7 says the logarithm of base of the m to the r exponent is r times logarithm of base a of m. Okay, guys, this is important. You understand it when you write the word log, you put the parentheses because it's similar to the function notation. There are a lot of people that omit this parenthesis. You put logarithm 2 like that. Everyone understands very well. However, no, it's strictly if you put the parenthesis because it's a function notation. Nobody write f of x like that. It's crazy. Okay, the parenthesis, those I highly recommend mandatory. Always to indicate the argument of the logarithm. Okay. So using that property, I can expand like that. Logarithm of base 5 of x. And what about the exponent 5? I put in the front as a 5 using the property 7. Minus 6 logarithm of base 5 of y. Done. End the story. This is the idea. Expand this logarithm and several logarithms, and the exponent you put as a factor. Boom. One more example, more complicated. Suppose you have logarithm base, bueno, logaritmo no, LM, que es natural, the calculus. N to the 5th, N to the 8, divided by x to the 6, y to the 7. Same operation, expand. We have 1, 2, 3, 4 expression, and you expand in 4 expression. The first one is ln m, and the exponent goes to the front like a factor, multiplication by 5, plus everything in the numerator is positive, 8 ln of m. Everything in the denominator is negative, 6 ln x minus 7 ln of y. End the story. Okay? And similar, we are doing the opposite operation. We are doing the opposite, completely backward, in which, for example, you, instead of expand, condensing. So, for example, let's give this example 3 times logarithm base 6 of x plus 5 logarithm base 6 of x minus 6. And the question says express this expression called as a single, only one logarithm. So now you apply the property number 5. Yeah, I know that the property number 5 because it's positive. Look, property number 5, where is this? Here, over there. This property number 5, when it's positive, you condense it like a multiplication. And the multiplication is you express only one logarithm. Guys, by the way, the base must be the same. See, it's 6, 6 is okay. See, 6 and 5, no, okay. So that property is only valid but the base of the logarithm is the same. Entonces, x to the third power inside the parenthesis. Look, that 3 go here, like exponent, and this 5 go here, like exponent. Multiplication, x minus 6 to the fifth power. Boom, final answer. Condensing in only one logarithm. Do you see or no? Clear or confusing? Clear or confusing? Okay, entonces now, motivation. Okay. Do you remember the last class we finished the class in one equation that we cannot solve it, no? We cannot solve it because we cannot apply common base. But now we are ready to solve it. We are ready to solve it now. What's going on, carajo? ¿Qué le pasa a esta mierda? Okay, don't worry. Okay, frozen. No. Okay. Okay, we finished the class with this example. Hey, what's going on? Wow, frozen. The whiteboard. Okay. Okay, there you go. Now respond. Okay. Okay, suppose this example. 2 to the x equal 3. This was impossible solving because you cannot find the common base. But using the tool of the logarithm, we apply logarithm on both sides. We apply logarithm. What kind? Standard. Maybe log or ln, because it's the logarithm that we can put in the calculator. And so you apply the property number 7, and the property number 7 allow me this x go to the front as a factor. Finally, you see that magically, this is science fiction. This original equation, this exponential equation, is converting to linear equation. Because actually, look like we are, but el logarithm 2 and logarithm 3 is a number que we can put in the calculator. So now it's similar to you, for example, you have an equation like that, 2x equal 3 divided by 2 both sides, x equal 3 over 2. Exactly the same we are doing, but no, using logarithm, of course. It's log divided by logarithm 2 both sides. Entonces x alone, que es my answer, is logarithm 3 divided by logarithm 2. Entonces, this kind of problem. Okay, introduction. We continue next time. We have two kinds of the exponential equation. The easy. You can express both sides using common base. Oh, exactly we are doing last class. But you have complicated, in which you cannot. And the only possibility you have to solving is apply logarithm on both sides. Apply the property of the logarithm and solve for x. And now, this is the exact answer. This is the exact answer. However, in the test, normally is I ask you the approximation answer using maybe 4 decimal place to say, now this is a moment that we practice in the next class in which in your calculator, remember the key log, you typing, this is the display, you typing here log, parenthesis. When you click here, you press the key, automatically you put log, parenthesis, you put 3, close the parenthesis, because you have here close the parenthesis, open the parenthesis on the calculator, divided by the key division, divided by division, press the key again, log of 2, bang, and you press enter. And when you press enter in the display, you can see that number is 1.58 49, and continue. Bam, 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 bam. But I want only 1, 2, 3, and 4 decimal places. Okay? This is the idea that we start ending the next class. So everyone, please bring the calculator, because you don't bring the calculator, you lost that information. It's mandatory in the test use a calculator, because that function is impossible to compute by hand. Okay? Super good? Super good or super bad? Everyone follow me? Okay. Okay, guys. Stop recording.